Hello, my dear students and viewers. I welcome you all in the first lecture of the course of A Primer to Mathematical Optimization. In this lecture, I will describe a brief history and important times on the development of optimization theory. In our daily lives, we continually require to select the best alternative or the ideal course of action. Today, in this era of fast moving academic and realistic research, we know that a number of optimization problems arise across economics and technology. Leonard Euler quoted once, "Nothing takes place in the world whose meaning is not that of maximum and minimum." Leonard Euler was a Swiss mathematician and is known as the most productive mathematician of all times, whose work consists of 81 quarto volumes, and was one of the first person to capture the importance of optimization theory. Wrote once that whatever human paradigm is manifest, it usually reflects the behavior of maximization and minimization. Hence, there are no doubts at all that natural phenomena can be explained by means of the methods of maximization or minimization. In fact, another great mathematician, Pafnuty Lovisevichev, also quoted that most practical questions can be reduced to problems of largest and smallest magnitude, and it is only by solving these problems we can satisfy the requirements of practice, which always seeks the best, the most convenient. In mathematics, the study of optimization problems began 25 centuries ago. From a long time, there was no uniform ways of tackling problems of finding extrema. The first general methods towards this direction were created about just 300 years ago from now, at the time of the formation of mathematical analysis. Optimization, is a field of mathematics that arose out of the interplay between calculus and geometry. Once geometry is involved in the development of some field of study, then that field must involve ultimate truth, because Plato, a Greek philosopher and a person who established the first institution of higher learning on the European continent, quoted once that geometry draws the soul towards truth. Apart from geometry, mathematical analysis, linear algebra are the fields that are inextricably linked to the development of optimization theories. In fact, it was necessary to create a new field of mathematical analysis known as convex analysis to enrich the theories of optimization and to solve several practical optimization problems in economics. During the development of optimization theory, it was found that many laws of nature can be derived from a principle called variational principle. According to these principles, given any collection of admissible motions, what distinguishes the actual motion of a mechanical system is that it maximizes or minimizes certain quantities. Does the rules of nature by birth or by creation follow some kind of maxima or minima? The oldest known problem in optimization is possibly the Dido's problem. Dido was a Phoenician princess fleeing from persecution by her brother. Dido set off westward along the Mediterranean shore in search of a haven. A certain spot on the coast of Bay of Tunis caught her fancy. Dido negotiated the sale of land with the local leader, whose name was Arv. She asked for very little land, as much as could be encircled with a bull's hide or bull's skin. Dido managed to persuade Arv, and a local deal was struck. Dido then cut bull's hide into narrow thin strips, tied the strips together, and then enclosed a large tract of land in the shore of Mediterranean. On this land she built a fortress, and near it the city of Carthage. Carthage is a Phoenician term whose English name is New Town. Now question comes mathematically, how much land then can one enclose by a bull's height? Mathematically, among all closed plane curves of a given perimeter, find the one that encloses the largest area. In today's mathematical development, this problem is easy to solve. Answer is obviously a circle. However, the term, curve, length, area, these were found almost after 2000 years of Dido. Dido solved this isoperimetric problem on 900 BC. Since then, several geometrical problems of maxima and minima were posed time to time and solved without the help of calculus. Let me mention another ancient optimization problem which is found in Euclid's element. Euclid's Elements is the first scientific monograph and textbook in the history of mankind, which was written in the 4th century before Christ, and there is just one maximum problem. In modern formulation, the problem is as follows, that in a given triangle ABC, inscribe a parallelogram ADEF where EF is parallel to the side AB and the line segment DE is parallel to the side AC. Find the parallelogram ADEF which is having the maximum most area. This problem you might have all solved in high school level and you all know the answer for it. I am keeping it as a home task. Let you recall the solution for this problem. Acta Eruditorum, the first scientific journal, began publication in the year of 1682. In the June 1696 issue of this journal, there appeared a note by the famous Swiss scholar Johann Bernoulli with the intriguing title that a new problem that mathematicians are invited to solve. The problem is the following. Let 2 points A and B be given in the vertical plane. Find the curve that a particle M moving on a path AMB on the vertical plane must follow such that starting from A, it reaches B in the shortest time under its own gravity. This problem is known as Brachistochrone problem. The word Brachistochrone has Greek origin whose English equivalence is shortest time. The answer to this problem is not a straight line because the particle A moves under the gravitational force. The answer is not also a circle, a circular path, but a cycloid. Galileo also have posed and solved several such types of problems for the natural phenomenon of falling bodies. In the next, let me mention a crude chronology of the key events and important times in the development of optimization theory. The oldest known optimization problem that I have already mentioned is the Dido's problem, which was solved in 900 before Christ. This Dido's problem is eventually found in a Latin epic poem called Aeneid, and Aeneid was written by a poet Virgil between 29 and 19 BC. In ancient times, before 300 BC, Greek mathematicians solved some optimization problems that are related to their geometrical studies. Greek people are all known for studies of geometry. In 300 BC, Euclid considered the minimal distance between a point and a line. He also figured out that a square has the greatest area among the rectangles with a given total perimeter. Around 100 BC, Heron proved in Catoprica that a light ray, after reflecting from a mirror, travels between 2 points through the path with the shortest length. At the beginning of 17th century, there arose the need to find some general methods of investigating extremal problems. René Descartes attempted to find algebraic means to find maxima and minima. Pierre de Fermat was the first to employ his method, what we now call differential calculus. According to his own words, he had discovered his method to find extrema as early as 1629 and possibly published in the year of 1636. Fermat showed that at the extreme point, that means at a point of local maximum or a local minimum, the gradient of the function must be vanishing. Surprisingly, calculus was developed in 1736 by Sir Isaac Newton and separately by Gottfried Wilhelm Leibniz in the year of 1684. Leibniz in fact found optimality conditions for functions of one variable. He derived the first order necessary condition for optimum is the derivative is equal to 0 at that point, and also used the second differential to distinguish between maximum and minimum. In the year of 1696 that I have mentioned, in Acta Eruditorium, Johann and Jacob Bernoulli, two Bernoulli brothers, studied the Brachistochrone problem. In 1746, the principle of least action to explain physical phenomena was formulated by Maupertuis. Next, the year 1762 is one of the prime year in the development of optimization theory, in which year Lagrange deduced the necessary optimality condition for constrained optimization problems for multivariable functions. To honor the work of Lagrange, Mathematical Programming Society and the Society of Industrial and Applied Mathematics, SIAM, introduced the Lagrange prize in continuous optimization, and this prize was established in the year of 2002. And to be eligible for this prize, the work must be either a paper or a book consisting chiefly of original results which has appeared in the 6 calendar years preceding the year in which the award is made. In the year of 1784, Monge investigated a combinatorial optimization problem which is known today as transportation problem. In the year of 1806, Adrian Mary Legendre presented the least square method, which has broad applications in linear regression, signal processing, statistics, and curve fitting. Carl Friedrich Gauss also claimed to have invented the least square method. In the year of 1826, Fourier formulated optimization problems with linear functions for solving problems arising in mechanics and probability theory. 1847 is an important year in which Augustin Louis Cauchy presented one of the most famous and widely used optimization technique, that is the steepest descent method or the gradient method for optimization. Julius Farkas presented his famous lemma for linear inequalities in the year of 1902, which can be used to prove the famous Karush-Kuntakar optimality condition for constrained optimization. Julius Farkas was a famous Hungarian mathematician and theoretical physicist whose name is best known to optimizers and OR specialists because of his theory of linear inequalities. To honor his contribution in optimization theory, the Farkas Prize of Informs Optimization Society was established in the year of 2006 and is awarded annually at the Informs Fall National Meeting to a mid-career researcher for outstanding contributions to the field of optimization over the course of their career. Towards the end of the 19th century and the initial years of 20th century, there arose the need of analyzing convex sets and convex functions. Jensen introduced convex functions in the year of 1905, and the idea has already appeared in the works of J.S. Hadamard in the year of 1883 and O.L. Holder in 1889 and O. Stolz in the year of 1893. Minkowski obtained the first results on convex sets in the year of 1911. Brun published the earliest study on convex geometry in the year of 1887. In the year of 1917, the first book in optimization theory has been written by Harris Hancock, a professor of mathematics from the University of Cincinnati. The title of the book is Theory of Minima and Maxima. In the year of 1932, Menger presented a general formulation of the famous traveling salesman problem. In 1936, Mochkin wrote his PhD thesis where he lists only 42 papers before 1936 on linear inequality systems. This explicitly shows how meager the research effort was till the year of 1936. In the year of 1939, Kantorovich presented a linear programming model and also proposed an algorithm for solving it. In 1975, Kantorovich and Koopmans got the Nobel Memorial Prize in Economics for their contribution to linear programming. In fact, Leonid Hytalovich Kantorovich was awarded several varieties of prestigious prizes, including the Stalin Prize in 1949, the Lenin Prize in the year of 1965, and the Nobel Prize that I said in the year of 1975. In fact, he became full professor at the age of 22, and his first research article was published when he was just 16. For the mathematical programming community, he is undoubtedly the father of a new science of optimization, which includes standard mathematical programming and also responsible for the three breakthroughs in optimization. Those are linear programming in 1939, then general conditions of optimality in the year of 1940, and the functional analysis techniques for convergence analysis of optimization algorithm, which was proposed by him in between the years of 1939 and 1948. The first paper on the convergence of an iterative method for minimization of a quadratic functional was published by Kantorovich in the year of 1939. After the Second World War, optimization develops simultaneously with operations research. John von Neumann, a Hungarian-American mathematician, is an important person behind the development of operations research. In the year of 1944, Neumann and Morgenstern solved sequential decision problems by using the idea of dynamic programming. In the year of 1947, George Dantzig, who worked for US Air Force, presented the simplex method for solving linear programming problems. Around the same year, 1947, Neumann also established the theory of duality for linear programming problem. Exactly 2 years after the first publication of the simplex method, that is in the year of 1949, Koopmans organized the first conference on mathematical programming in Chicago, which was later counted as the number 0 conference in a sequence of mathematical programming conferences taking place till today. The number of papers presented in that 0 conference of mathematical programming was just 34. Next, in the year of 1951, Harold William Kuhn and Albert William Tucker reinvented optimality conditions for nonlinear optimization problems. Fred John in 1948 and William Carus in 1939 presented similar conditions earlier. The optimality condition of Kuhn and Tucker is widely and mostly used optimality condition in constraint optimization theory. As the optimality condition of Kuhn and Tucker was found to have derived by William Carus, thus this optimality condition is named as Carus-Kuhn-Tucker optimality condition, or in the abbreviated form just the KKT optimality condition. In the same year 1951, Harry Markowitz presented portfolio theory that is based on quadratic optimization. Harry Markowitz is an American economist who received the 1989 John von Neumann Theory Prize and the 1990 Nobel Memorial Prize in Economic Sciences. I must have also mentioned the prize received by Kuhn and Tucker. Kuhn and Tucker won the John von Neumann Theory Prize in 1980, and you know the John von Neumann Theory Prize is awarded annually to a scholar or scholars in case of joint work who has or have made fundamental sustained contributions to theory in operations research and the management sciences. To honor the work of Albert William Tucker, a prestigious prize has been announced in his name, and it is called as Tucker Prize, which was established in the year of 1985. Now, in the next of the chronology of the development of optimization theory, in the year of 1960, Joutentjig presented the methods of feasible directions to generalize the simplex method for nonlinear programming. Rosen, Wolf, and Powell also developed similar ideas. Interestingly, in the year of 1972, there appeared a research article in the Journal of Mathematical Programming entitled A New Algorithm for Optimization. In this article, authors did not reveal their names, and therefore author of this article is anonymous. Professor Henry Olkowich from the University of Waterloo mentioned that this paper could minimize anything and everything. Before mentioning this 1972 paper, I must have mentioned that the Mathematical Programming Journal was founded in the year of 1970 to provide a discussion forum for researchers in the optimization field. In the year of 1973, based on the activities by George Dantzig, Albert Tucker, Philip Wolff, and others, the Mathematical Programming Society was founded with George Dantzig as its first president. The Mathematical Optimization Society, known as the Mathematical Programming Society until the year of 2010, and is an international association of researchers active in optimization theory and applications. The Mathematical Optimization Society is popularly abbreviated as MOS. It encourages the research, development, and use of optimization, including mathematical theory, software implementation, and practical applications. Around 1975 or afterwards, researchers attempted to identify the efficiency of the simplex method for solving linear programming problems. And it was the year of 1979 where Leonid Jendrokovich-Khachiyan found that in the worst case, simplex method can have exponential time complexity, and hence he presented the first polynomial time algorithm for linear programming problem, and that method is named as the ellipsoid method. For outstanding papers in the area of discrete mathematics, particularly his 1979 article, A Polynomial Algorithm in Linear Programming, Leonid Jendrikovich-Khachiyan was awarded the prestigious Fulkerson Prize by Mathematical Programming Society and the American Mathematical Society. The Fulkerson Prize, is for outstanding papers in the area of discrete mathematics, and which is sponsored jointly by Mathematical Programming Society and American Mathematical Society. To honor Professor Khachiyan's contribution in optimization, Informs Optimization Society started the Khasian Prize in the year of 2010, and it is awarded annually at the fall Informs annual meeting to an individual or a team for lifetime achievements in the area of optimization. After the appearance of the Khasian's paper in the year of 1984, there appeared a big revolution in the optimization theory and methods by the interior point methods of Narendra Krishna Karmarkar. Interestingly, a single article of Narendra Krishna Karmarkar entitled A New Polynomial Time Algorithm for Linear Programming is having citation more than 8,000. After the appearance of the interior point method of Narendra Karmarkar, the interior point method has been applied in several structured optimization problems like quadratic programming problems, semi-definite programming problems, and so on. In the history of development of optimization methods during 1960s and 70s, the complexity analysis of algorithms have been developed and that began to influence the theory of optimization also. The 80s, as computers become more efficient, heuristic algorithms for global optimization and large-scale optimization problems began to gain popularity. In 90s, the interior point methods have been applied to solve semi-definite optimization problems. In the current century, researchers have been attempting to check if the optimization algorithms for single objective optimization problems can be employed to solve optimization problems with two or more objective functions. For extensive details on the history of the development of optimization theory, I would like to refer you the following references, together with an interesting article written by Boris Polyak, which is appeared in the Journal of Mathematical Programming, and also the article and the book and a very interesting article by George Danzi. Before closing the lecture, let me tell some stories about how various common terms in optimization theory or general mathematical programming arose. I will quote a few lines from this article of George Danzig. Those are as follows. First, let me tell you why the term programming in mathematical programming or linear programming or non-linear programming. The word programming is not related to computer coding or computer programming. The word programming came in the following way. The US military refers to their various plans or proposed schedules of training, logical supply and deployment of combat units as a program. When George Danzig had first analyzed the Air Force planning problem and saw that it could be formulated as a system of linear inequalities, then Danzig called his first research article entitled Programming in a Linear Structure. The word programming came from the US military's commonly used term program for planning or scheduling of training. In the summer of 1948, Koopmans and George Bernard Danzig visited the RAND Corporation, United States, which is an organization formed immediately after Second World War to connect military planning with research and development decisions. During their visit to R&D Corporation, one day they took a walk near the Santa Monica beach, and during their walk, Danzig was explaining his method for linear programming to Koopmans. After listening Danzig's description, Koopmans said, "Why not shorten programming in a linear structure to linear programming?" Since then, programming in a linear structure is shortened to linear programming. Later on that same day, Danzig gave a talk at RAND Corporation entitled Linear Programming, not his original title Programming in a Linear Structure. The term mathematical programming, is due to Robert Dorfman, who felt as early as 1949 that the term linear programming was too restrictive. In the 1950s, apart from linear programming, several new research directions in the area of extremal problems have been developed, which are summarized today under this keyword mathematical programming. Mathematical programming is also responsible for many terms which are now standard in mathematical literature. The terms like argmin, argmax, lexicomax, lexicomean, all these terms are terms being used while the development of mathematical programming. The terms primal problem and the dual problem came in the following way. It is very interesting to learn that the term dual problem was introduced before the term primal problem. It came out in the following way. W. Orchard Hayes, who is responsible for the first commercial grade linear programming software, requested Danzig at R&D Corporation one day around 1954 that they need a word that stands for the original problem of which the problem that they were talking about is the dual. George Bernard Danzig requested his father to give a name to the original problem of which the given problem is the dual. Danzig's father name was Tobias. Tobias Danzig was also a mathematician and an author of several books popularizing the history of mathematics. Tobias Danzig never took interest on linear programming, although George Danzig several times attempted to make his father to be involved in the development of linear programming. But on the occasion when George Danzig requested many times to his father to give a name for the original problem of which the given problem is the dual, Tobias Danzig took a bit interest. Tobias suggested the name of the original problem as the primal problem, since a natural antonym of the Latin word dual is primal. George Danzig mentioned that this wording dual problem due to his father, and it was Tobias' one and only one contribution to linear programming. As several times I have referred the term linear programming, let me tell you the general structure of a linear programming problem, which is commonly abbreviated by LPP. LPP is an optimization problem involving linear functions subject to linear inequalities. That is, in an LPP, we need to minimize or maximize a linear function C transpose X, where C is an n-dimensional vector, X is an n-dimensional generic variable, subject to inequalities A transpose X less than equal to some constant Bi for I equals to 1 to a finitely many inequalities. Here AI is an n-dimensional vector, Bi is a real number. This is a general structure of linear programming problem. A general optimization problem that we shall endeavor in the entire course to solve is the following problem: minimization or maximization of a function of n variables subject to some constraint set C, which is a non-empty subset of the n-dimensional Euclidean space. This is a general optimization problem which we shall try to solve in the entire course. The problem for the entire course is then very simple. This is the problem we will attempt to solve, where we will pre-assume that this function f is continuously differentiable and the set C, which we call as the constraint set because X is constrained to lie inside the set C, and thus the name constraint set. The constraint set is usually assumed to be given by a structured manner through some inequalities like some function gix less than equal to 0, let's suppose m many, together with some equalities given by functions aj's. J is ranging from 1 to say till p. The function f for an optimization problem is referred as the objective function, and the functions, these gi's or hj's, they are referred as the constraint functions. For a linear programming problem, we notice that the objective function fx is having this expression C transpose x, and gix, this constraint function, is having the expression ai transpose x minus bi. In an optimization problem, if any of the functions fx, gix or hjx is not linear up to a constant, then that problem is referred as a nonlinear programming problem or NLP. In the entire course, we shall thus attempt to solve an NLP where the objective function and the constant functions will be assumed to be sufficiently smooth. Although in this course I aim to give a primer on mathematical optimization, due to the time bound about 30 hours for this course, I will miss out two important topics of optimization. Those are methods for linear programming problems and non-smooth optimization. In fact, I will not be able to touch upon these two topics, linear programming and non-smooth optimization. During the discussion of methods of optimization, I will also not be able to cover evolutionary algorithms, which are generic population-based meta-heuristic optimization algorithms that use mechanisms inspired by biological evolution such as reproduction, mutation, recombination, and selection. In fact, the development of the whole mathematical optimization theory and applications is so vast and elegant today that several universities across the globe have started opening a new discipline called the School of Decision Sciences, where extensively the methods of optimization being used. So certainly I will not be able to even touch upon all the topics of optimization and its applications in a single course about 30 hours. If however I get a chance later, I will certainly cover these two topics in a different course. So neatly, this course is a primer on nonlinear optimization with smooth or continuously differentiable functions. Last but not the least, this course is not a course of operations research or operational research or the popular abbreviation OR. OR is the science of decision making, the science of choice. But optimization is a field of core mathematics whose development is not at all dependent on human decision making or human choice. In fact, regarding the distinguishing characteristic of OR, two professors of business analytics and operations research from University of Maryland, United States, Professor Shaul I. Goss and Arjang A. Asad, commented in this book that OR applies its scientific and technological base to resolving problems in which the human element is an active participant. OR is in fact an interdisciplinary branch of applied mathematics and formal science that makes use of methods like mathematical modeling, algorithms, and statistics to reach optimal or near optimal solutions to complex situations. Thus, in case you aim to learn topics of operations research, this course is not for you. Basically, a discussion of the mathematical results for optimization theory and methods is the prime aim of this course. We shall start the first section of this course in the next lecture, where the tools of linear algebra that are required in the entire course will be detailed. Thank you all for all of your kind presence.